Okay, now that we know how to multiply matrices, you might be wondering why we spent so much time talking about that. And the answer to that is, let's consider the following problem. Let's suppose we want to write some computer programs that are dealing with graphs, and we want to find out certain information about graphs. The question is how would one store the graphs internally in the computer? Now, what I've done over here is I've given you two graphs, and I want you to notice that they're actually the same graph. Each graph has 5 vertices in them. You will notice that this graph over here is an undirected graph, which in theory what that means is that if I'm at any particular point on the graph, for example, if I am at the vertex labeled 1, I can travel to 2, and if I'm at 2, I can travel to 1. If I'm at 1, I can go to 3, and if I'm at 3, I can go back. Here it's a directed graph, and you can see that the edges have arrows on them. So over here, you'll notice that between 1 and 2, there are actually 2 arrows, and one is going one way and one is going the other. So I can travel back and forth between these two. But you'll notice that between nodes 1 and 3, there's only an arrow going towards 3. If I'm in 1, I can go to 3, but once I'm in 3, I can't get back to 1. And that's a property of the directed graph. So the first question that we want to talk about here is I want to talk about what would be a convenient way to represent either one of these inside of a computer program. And the answer to that is with what's called an adjacency matrix. You knew that matrices were going to come back sooner or later. Well, they are back. And the concept here is actually very simple. First we'll look at the undirected graph, and we'll note that we have a graph that has 5 vertices in it. So what I'm going to do is I'm going to create a 5 by 5 matrix. And what's going to happen is what I'm going to be doing is in the I and jth entry here, remember the ith row and the jth column, I will put a 1 if it's possible to go from I to j. In other words, over here I am in the first row, and I note that I can go from 1 to 2. So what I'm going to do over here is in row 1, entry 2, I'm going to put a 1. Okay? Over here in 1, 1, I'm going to put a 0. You may recall in your book, a lot of times they draw graphs, or they give you the example of a graph where there's a loop. So here's an example of a loop. Okay, and that's an edge that starts and ends at the same vertices. Okay, so if this were part of the graph, which I don't want it to be, but if it were, then that would say that if I'm in 1, I can travel to 1. Okay, and in which case this would then have a 1 over here and not a 0. But I don't find that graphs that have loops in them are very interesting, and I haven't been discussing them in the videos, although they certainly do make reference to them in your book, okay? But if you just follow the logic of what's going on here, if I'm in node 1, there's no loop, but I can go to 2, so that's why there's a 1 here. I can go to 3, so there would be a 1 here. There's no way to get from 1 to 4, okay, or 1 is not connected directly to 4. And 1 is not connected directly to 5. So again, if you realize here, looking across at the first row, wherever I see a 1, that is indicating that there is a connection between 1 and that respective vertices. There's from 1 to 2, and there's from 1 to 3. And I'm going to repeat the same thing for all of the entries down here. So there is an entry from 2 to 1, and then I can see 2 is not connected to anything else. If I look at 3, 3 is connected to 1. 3 is connected to 4. And 3 is connected to 5. We can see that 4 is connected to 3, so there'd be a 1 here, but there'd be zeros here. And we can see that 5 is connected to 3, so there's a 1 here, zeros there. And we can see that what we have here is this is the adjacency matrix for this graph here. And I hope you could also see that if I were to just give you the adjacency matrix and ask you what undirected graph this corresponds to, given this information, you could draw this. I believe there are homework problems that do exactly that. Now, that is with the undirected graph. Here we come over and we consider we do the same thing with the directed graph. It is not difficult to see how we would do this here. Again, we only put ones when there is a direction going to it, okay? One thing that we'll note about this matrix over here is we will note that this is what's called a symmetric matrix. And what that means is that Aij is in fact equal to Aji. Because these lines here go in both directions, if I can go from 1 to 3, that means I can go from 3 to 1, okay? And what it means to be symmetric is it means that if I were to draw a line right down this diagonal, the upper right-hand half of the matrix would be the mirror image of the lower left-hand one. But when I come over here and I look at directed graphs, there isn't any symmetry. For example, notice I can go from 1 to 3, but I can't go from 3 to 1. Well, that says to me that A13 is not going to equal A31. Okay? In fact, A13, I can go from 1 to 3. This over here is going to be a 1, but I can't go from 3 to 1. That over there is going to be a 0. So anyway, let's just go ahead and make the adjacency matrix here. So I get a 0 here. That's going from 1 to 1. I can go from 1 to 2. I can go from 1 to 3. I can't go from 1 to 4 or 5. I can go from 2 to 1. And then I can't do anything else there. So far it still just looks like the other matrix. But now things are going to get a little bit different. I can go from 3 to 4. And I can go from 3 to 5. So over here, I'm going to get a 1 and a 1. But that's it. Okay, from 3, I can't go anyplace else. And I can see from 4, I can't go from 4 to anywhere. So they're going to be zeros all the way across here. And now from 5, it looks like I can go back to 3. So over here, this is the adjacency matrix for this graph over here. Everybody okay with that? All right, let's keep this diagram up here. I'll move it right over there. Let's get this out of the way. You don't need to see that. All right, let's just move this over a little bit. And now what I'd like to do is I'd like to consider the following problem. Suppose I'm starting off here at vertice number 1. Start at vertex 1. And I wish to take a walk. And the question I have where will I be if I restrict myself to a path of length 2? Okay, so first of all, I could certainly start here at 1, and I could go to 2 and come back to 1. I could start here at 1, I could go 3 and come back to 1. These are all of length 2. I could go from 1 to 3 and then to 5 I could go from 1 to 3 and then to 4. Okay? If I start at 4, I could go 4, 3, 4. I could go 4, 3, 5. I could go 4, 3, 1. Okay? So I think you get the idea there. But let's think about something else here. Suppose I were to say how many paths of length 2 start and end at 1. Well, think about it. That means that I start at vertex 1, I go somewhere, and then I come back to 1. Okay? This is a 1. That's a 1. So basically what that's saying is I could go from 1 to 1 and back to 1. I could go from 1 to 2 and back to 1. 1 to 3 and back to 1. I could go from 1 to 4 and back to 1. Or I could go from 1 to 5 and back to 1. Okay? Well, let's think about this. We know, looking at the graph, we know that some of these, there is no path to that. And if we were to put that in terms of the adjacency matrix, some of these paths are going to have zeros in them. For example, if I see 1 to 1, there's a 0 on that one. Okay? 1 to 2 and 1 to 3 are fine, but there's no 1 to 4, and there's no 1 to 5. Okay? In other words, if I consider some A from 1 to J, okay, we know that this is non-zero if J is equal to 2 or 3. Okay? And remember, if we want to start at 1 and we want to end at 1, this is going to be some A, I, 1J. And then this over here is going to be A, J, and it takes us back to 1. Okay? So what we basically are looking at over here is think about it. We're talking about going from 1. This one right over here is going from 1 to 1 and then from 1 to 1. This one is going from 1 to 2 and then 2 to 1. 1 to 3 and 3 to 1. 1 to 4, 4 to 1. 1, 4, A, 4, 1. And then A, 1, 5, A, 5, 1. Now again, notice that what we said for 2 and 3, these are non-zero. These are 0. But the point is the total way to start at 1 and finish at 1 in 2 hops would just be to add these up. Okay? And the thing to notice about this that's kind of cool is if you come back over here to the adjacency matrix, and let's call this A, okay, this quantity right over here, think about going A times A, and what this quantity is it's actually this row times this column right here, which is real. Remember, this is A11, A12, A13, A14, A15. This is A11, A21, A31, A41, and A51. Well, this is pretty cool, because here's what that means. If I come over here, and here's A, 1, 0, 0, 1, 1. And what I'm going to do is I'm going to multiply this matrix. So this is A, and I'm going to multiply it times itself. And this is a square matrix, so I can do that. So let's go ahead and do that. Well, okay, I've got to go this times that. Okay, and if I go this times that, I'm going to get a 1 plus 1. I'm going to get a 2 over here. And now I'm going to go this times that. And if I go this row times this column, it looks like I'm going to get a 0. And now I'm going to go this row times that. See, I can do this quickly because I noticed that the non-zero entries here are in 2 and 3, and over here in 2 and 3 there's zeros. That's going to give me a 0. I come over here and I go this times that, and I see, well, that one's going to match that, so there'll be a 1 there. And now I come over here on the last one and I go this times that, and I'm going to get a 1. And by the way, just let's check our results. We're saying that there are exactly 2 ways to start at 1 and finish at 1. And if we come over here and we look at the graph, we can go, oh yeah, I can go from 1 to 2 to 1, and I can go from 1 to 3 to 1. Okay, there's exactly one path that takes me from 1 to 4 in 2 steps. And that's it right there, 1 to 3 to 4. And there's one that takes me from 1 to 5. 1, 3, 5. So let's complete this graph, this thing now. So I'm going to come over here now and I'm going to multiply this times that. That's a 0. And in fact, I can see over here as I'm going to multiply this times this, the only ones where I'm going to get non-zero entries is wherever there is here, I've got a non-zero entry in the first one. I've got to look here where I get non-zero entries. So it's going to be there and there. So that's going to be a 1 and a 1. And these will be zeros. Over here, okay, it's a little more complicated here, but I can see when I multiply this one times that one, there are no places where there are 1s that agree. Notice at position 2 and 3, I've got 0. Position 2 and 3s, I've got 1s there. This is going to be a 0. I come over here, and this is going to be 1 plus 1 plus 1. This is going to be 3. Okay. No. I think I've made a mistake here. I have made a mistake here. I am going this row times this gives me a 0. I'm going to go this row times this. This is going to give me a 1. So that's a mistake, that 3. That should be a 1. Okay, now when I go this third row times this third column, there I get the 3. I'm going to go this third row times this column here. That's going to be a 0. And I'm going to go this third row times this one here. That is also going to be a 0. I come over here. So there's a 1 in the third position. There's a 1 in the third position here. So there's a 1 there. That's going to be 0, 0. Okay, I'm coming over here in the third position. That's in the third position, 1, 1. And I'm going to come down here, and it's the same thing again. There would be a 1 there. There would be, when I go this times that, that's a 0. When I go this times that, that's going to be a 0. This times that is going to be a 1, and that's a 1. And this matrix here is A squared. Let's look at some of these things. Well, this is 1, 2, 3, 1, 2, 3. It's telling me that there are 3 different ways to start at node 3 and end at node 3 in 2 hops. 3 ways. Well, that would be 3 to 1 and 1 to 3 is 1. 3 to 5 and 5 to 3 is 2. 3 to 4 and 4 to 3 is 3. Okay? That's starting at 3 and ending at 3. Notice there's one way to start at 2 and end in 3. Oh, look at that. 2 to 1 and 1 to 3. Everybody see that? Kind of cool. Now what I can do is I can extend this to even 3 hops. If I come over here and I start off with A, and now, so here's A, and I multiply this by A squared. And again, notice there's square matrices. I can do this. This is A squared. What I'm going to get over here is a matrix that I'm going to call A cubed. And let's figure this out. So I'm going to go this times that. And notice over here, here's where the non-zero entries are, but those are 0 entries over here. This is going to be 0. Okay? If I come over here and I go this times that, it looks like I'm going to get 1 times 1 plus 1 plus 1. I get a 2. If I go this times that, ooh, I'm going to get 1 times 1 plus 1 times 3. This is a 4. If I come over here and I go this times that, I'm going to get a 0. And I'm going to get a 0. Before we do the rest of this, let's think about what this is telling me. It's telling me that if I start at vertex 1, there are 2 ways that I can get to vertex 2 in 3 hops. Well, if I start here, I can go 1, 2, 3. That's one way to do it. Or if I start here, I can go 1, 2, 3. That will do it as well. It's telling me that there are 4 ways to go from vertex 1 to vertex 3 in 3 hops. 4 ways. Let's see if we can figure this out. If I start at 1, I can go 1, 2, 3. That's one way. If I start here, I can go 1, 2, 3. That's 2 ways. If I start here, I can go 1, 2, 3. That's 3 ways. Where's the 4th way? I can go 1, 2, hang on. I'm lost now. If I can go from 1 to 3 in 4 ways. 1, 2, 3. Ah, I think I see it. I can go start 1, 2, 3. That's one way. 1, 2, 3. That's 2 ways. 1, 2, 3. That's 3 ways. And then 1, 2, 3. That's 4 ways. All right, that works. So now let's just continue with our matrix here. And now I've got to multiply this row times this column, this column, this column, this column, this column. We can see right over here that there's only a 1 in the very first one. It's just basically going to take this whole row and copy it over here. I'm going to get 2, 0, 0, 1, 1. I leave it to you to verify what I just said. I come over here now. I'm going to multiply this row times this column. That's going to be 2 plus 1 is 4. I'm going to come over here, and over here this will be a 0. I'm going to come over here and do this times this one. That's going to be a 0. I'm going to do this row times this one right here, and that's going to be 1 plus 1 is 3. And I'm going to come over here, and it's going to be this row times this row right over here, and again, that's going to be 3. I come over here, and what's going to happen is that's going to be 0 for this one here. I come over here and I do this one for this one, and it's going to be a 1. I come over here and do this one, and that's going to be a 3, and then 0, 0. And the same thing over here. Okay, notice this is the same row as this. So I think what it's going to do is it will just repeat this row 0, 1, 3, 0, 0. And notice what this is showing me here is that in 3 hops, okay, it's showing me how many pads there are between these respective vertices. For example, this number right here tells me that I can start in vertex 3 and end up in vertex 1 4 different ways in 3 hops. 4 different ways. If I start over here in 3 hops, I can go 1, 2, 3. I can go 1, 2, 3. I can go 1, 2, 3. And I can go 1, 2, 3. 4 different ways. Okay? And we can continue this on and on for 4 hops, 5 hops, 6 hops. We'll finish up this section here just by showing you can do the same sort of calculation with a directed graph. Again, you can see I've gone back here to the graph that we were working with before. Recall, here's the undirected version of it. Here's the directed version of it. Here was the adjacency matrix for the undirected graph. Here's the adjacency matrix for the directed graph. So we're going to work with this one right here. So we're going to start off with our matrix A, which is going to be 0, 1, 1, 0, 0. Okay, so this is the matrix A, and we're going to multiply it again by the matrix A. Like that. So when I come over and multiply these things, I'm going to multiply this times that, and it looks like I'll get a 1. And then I'm going to come over here and I'm going to multiply this times this, and it looks like I'm going to get a 0. And likewise, if I go, notice I've got 1, 1 here. Here I've got 0, 0, so that's going to be a 0. Over here I've got 1, 1. I've got to look at it over here. That's going to give me a 1. 1, 1 here, and I'm going to multiply to that. It's going to give me a 1. So this is saying in 2 hops where I can go to from 1. Let's think about that. Well, I can go from 1 to 1 in 2 hops. It looks like I can go to 1 to 4 in 2 hops. And it looks like I can go 1 to 5 in 2 hops. So that makes sense. And let's just continue with the rest of these. So I'm going to be coming across here and multiplying this times this and this and this and this. Notice there's only a 1 here. So it's basically going to copy this row here. So I'm going to get a 0, 1, 1, 0, 0. I'm going to come over here and go this times these columns. And now since there's a 1, 1 over here, I just have to look at wherever there are numbers in the last 2 entries here. That's going to be a 0, 0. Okay, over here it's going to go 1 times 0 plus 1 times 1 is going to be a 1 there. Okay, then it's going to be 0, 0. Here, this is going to be zeros all the way across. And over here, it is going to be, it's going to match, there's only a 1 in the middle element here. So it's only going to match columns where there's a 1 in the middle element. That's going to be right over here. So when I go this times this, I get 0, 0, 0. When I come over here and go this times that, I get a 1. and I come over there and I go this times that, and I get a 1. So this thing over here, this is a squared. Okay, so for example, I can start in node 5 and end up in node 4. In 2 hops, there's one way to do it. So if I start in 5, I can go to 3, and then I can come back to 4. There's one way to do that. If I start in node 5, there's one way to get back to 5 in 2 hops. So you can see that this is consistent with the drawing we've done here. And again, what we can do, if we wanted to, we could calculate A3, and we could calculate A4, etc., etc., etc. So conceptually, there's not much difference between the directed graph and the undirected graph.